Turbulence is characterized by irregular, random flow variations in velocity and direction, and is the single most relevant topic of fluid dynamics, simply because it is the most prevalent. Turbulent flow can be seen or experienced in every aspect of life and motion. Anything moving through the air creates an area of turbulence behind it. Laminar flow is easy to obtain information on and perform calculations on, while turbulent flow absolutely is not. Unfortunately, in practical situations, turbulent flow is much more likely to occur. Here are some quick examples of turbulence occurring in everyday situations. Boiling water, weather patterns and atmosphere, rising smoke, the flow of air around a moving golf ball, the flow of fluid around vehicles, such as an airplane, car, or submarine, and the flow of air around a traveling bullet. The most common way to determine if a flow will be turbulent is with use of the Reynolds number. For example, in a pipe, if the Reynolds number is 2100 or below, the flow will be laminar. The area in between 2100 and 4000 is known as the transition region, where the flow exhibits both properties. If it is above 4000, the flow will be turbulent. As can be seen from the structure of the Reynolds number, the greater the fluid velocity, the greater the value. Hence, a fluid starting at rest will have a Reynolds number at 0 and gradually transition towards turbulence as the fluid velocity increases. So why does turbulence even occur? How can it be measured? And what other aspects of turbulence are important to understand? These are questions that dozens of scientists have spent years trying to answer. Chaos theory is the most intriguing area of research for those looking to understand turbulence. It is a very new branch of physics using complex mathematics and computer models to understand previously unsolvable problems. The theory involves the behavior of nonlinear dynamic systems in response to known initial and boundary conditions. As can be seen in this video of a Lorenz model, minuscule variations in starting positions result in major variations in path. As we know, the flow of viscous fluids is governed by the Navier-Stokes equations. These equations rely heavily on initial and boundary conditions, making the flow of viscous fluids prime topics for researchers of chaos theory. Solving the Navier-Stokes equations for pressure and velocity profiles for viscous flow requires a prior knowledge of the boundary and initial conditions. Researchers speculate that, if the Navier-Stokes equations allow for chaotic behavior, then the state of the flow at times beyond the start time would be extremely sensitive to the initial conditions. This postulate, also known as the butterfly effect, states that an infinitesimally small variation in the initial conditions results in extremely large variations in the final result, as can also be seen in this video, resulting in turbulent flow around the obstacle. Future discoveries in the field of chaos theory will undoubtedly lead to a deeper understanding of turbulence. It may even be found that our current ad hoc ways of dealing with turbulence are unnecessary.